Welcome back, my dear students. In this video we will be discussing about the relationship between continuity and boundedness of a linear operator defined on a normed spaces. So theorem 2.7.9 continuity and boundedness. Continuity and boundedness. Let t from dt to y be a linear operator where bt subset of x and x and y are normed spaces. X comma y are normed spaces. Then first condition is t is continuous if and only if t is bounded. Second condition, if t is continuous at a single point, if t is continuous at a single point, it is continuous everywhere. It is continuous actually, which means that it is continuous at every point. So this is the theorem which connects continuity and boundedness. So theorem states that let T be a linear operator which is defined from d of t to y, where d of t is the domain of t, which is a subset of x, where x and y are normed spaces. Then t is continuous if and only if t is bounded. That is, t is bounded means t is continuous, and t is continuous implies t is bounded. And also the second property, which is actually a very important one, if t is continuous at a single point, then it is continuous everywhere. Okay, so which means that if t is continuous on a particular point, that is enough to establish that t is continuous everywhere. And using that, we can also state that if t is continuous at a single point, then t is continuous everywhere. If t is continuous, then t is bounded, which means that if t is continuous at a single point, then t can be considered as a bounded linear operator. That's it. Okay, so continuity at a single point implies the continuity of the function as a general and the boundedness of the function as well. So this simplifies the global property. This relates the global property of a function linear operator with respect to a single point. So boundedness and continuity are global property, which means that it's a property which relates to the set as a whole. But here we relate these two properties with regards to the properties associated with a single point. If t is continuous at a single point, then it is continuous everywhere. If it is continuous everywhere, then it is bounded. So the global property of linear operator relates to a local property, that is continuity at a single point. That's the statement. So we have to prove this part. In the first case, we have to prove that t is continuous implies t is bounded, and t is bounded implies t is continuous. So let's move on to the proof part of this theorem. Let's move on to the proof. So first consider the case when t is equal to 0, that is t is the 0 operator. Since 0 operator is always bounded and it is continuous, so the result is trivial. So the statement is trivial. So we do not have to prove, because the 0 operator is always continuous as well as bounded. So we only have to consider the case when t not equal to 0. So let t not equal to 0. Then clearly norm t not equal to 0 by the property of norm. So in this case we have to prove that t is continuous implies t is bounded, and t is bounded implies t is continuous. First assume that t is bounded. Okay, so we have to prove that t is actually continuous. So for that choose an x naught, an arbitrary x naught belongs to d of t, and let epsilon greater than 0, and take set of all x belongs to d of t such that norm of x minus x naught is actually less than delta, where we choose all of this, where delta is equal to epsilon by norm t. So we have taken an epsilon, then norm of tx minus tx naught by the linearity property, which can be written as t of x minus x naught by linearity. Now by the boundedness we have assumed that t is bounded, which means that norm of tx is actually less than or equal to norm t times norm x. Here instead of x we have x minus x naught. So by the boundedness property, this is actually less than or equal to norm t into norm x minus x naught by boundedness. Now we have already assumed that norm of x minus x naught is actually less than delta. So this is actually less than norm t into delta. So delta is actually taken as epsilon by norm t. So now you understood why we have chosen delta in such a way that delta is equal to epsilon by norm t, because we have to cancel this. So this is actually less than or equal to norm t into epsilon by norm t, which is equal to epsilon. So we have established that for every x element of d of t such that norm of x minus x naught less than delta, we can have norm of tx minus tx naught is less than epsilon. So for all x element of d of t such that norm of x minus x naught less than delta, we have norm of tx minus tx naught less than epsilon. Okay, so which means that t is continuous at x naught. Since x naught is arbitrary, since we have chosen x naught to be an arbitrary point, x naught is arbitrary, t is continuous at every point, any arbitrary point. So t is continuous at any point, so which means that t is continuous. So t is bounded implies t is continuous. That part is proved. Now we have to prove that, assume that t is continuous, then we have to prove that t is actually bounded. Now assume that t is actually continuous. So t is continuous. We have to prove that t is bounded. So this is our assumption. We have to prove that t is bounded. So by the definition of continuity, we have norm of Tx minus Tx naught is actually less than epsilon for all x belongs to d of t, satisfying norm of x minus x naught less than delta. Now take any y naught, any y not equal to 0 belongs to d of t, and set an element x as x is equal to x naught plus delta y by norm y. We can define such an element for every y element of d of t, y not equal to 0. We already have an x naught. We can define x as x is equal to x naught plus delta y by norm y. Then x minus x naught is equal to delta y by norm y, and norm of x minus x naught should be equal to norm of delta y by norm y. So delta is a positive constant. By using the definition of norm, which is equal to modulus of delta into norm y. Modulus of delta is equal to delta since delta is positive. So delta into norm y divided by norm y. So which is equal to delta. So norm of x minus x naught is actually delta. So x is elements such that norm of x minus x naught is actually equal to delta. We have to establish that t is bounded using this part, norm of tx minus tx naught less than epsilon. Using this. So take norm of tx minus tx naught by linearity property, which is equal to t into x minus x naught, t of x minus x naught, okay, by linearity property, okay, and x minus x naught can be written as delta y by norm y. So this can be written as, by our choice, t of delta y by norm y. Okay, so by the linearity property, delta is a constant, norm y is a constant, so delta by norm y is a constant. We can take it outside, which should be equal to norm of delta into norm y into t of y, since t is linear. Now using the properties of norm, we can take this constant outside. We can take it as outside, so we can write it as modulus of alpha delta norm y. Since delta is positive, norm y is positive, we do not need modulus, so which should be equal to delta by norm y. We do not need modulus because this quantity is positive, into norm ty. Now we adjust our condition so that here this continuous implies norm of tx minus tx naught less than epsilon for all x satisfying this condition. So an equality condition as well. Norm of, so I take collection of all x such that norm of tx minus tx naught less than or equal to epsilon for all x satisfying this less than or equal to delta. I am using this so because in order to establish the boundedness, the condition of boundedness is actually less than or equal to. So we need an equal to part as well. That's why I am using this equal to part as well. If I am proceeding only with less than part, we only get the less than part here. So the form of tx minus tx naught, which is equal to this less than epsilon. We need the less than or equal to part. That's why I am using I'm collecting all points such that the equal to part also holds. So norm of tx minus tx naught is less than or equal to epsilon, means norm of this part is less than or equal to epsilon. So which means that delta by norm y into norm of ty is actually less than or equal to epsilon. So norm of tx minus tx naught less than or equal to epsilon implies delta by norm y into norm of ty is actually less than or equal to epsilon. Now move this onto the right hand side. So we get this implies norm ty is actually less than or equal to epsilon by delta into norm y. Okay, so this means that norm of ty is actually less than or equal to some constant c, where c is equal to epsilon by delta into norm y. So norm of ty is actually less than or equal to c into norm y, which means that our operator t is actually bounded. We have chosen y such that y is an arbitrary element of d of t. We have already chosen here that y is an arbitrary element of d of t and y not equal to 0. From that, which also satisfies norm of t of y less than or equal to c into norm y. So here we need an equality part. That's why we chose our condition. We tweaked our condition a little bit. So this means that t is actually bounded. So t is bounded. So t is continuous implies bounded, and t is bounded implies continuous as well. So this establishes the theorem, first part of the theorem. Now moving on to the second part. Now move on to the second part. In the second part, we have to establish that. So second part, we have to prove that t is continuous at a single point implies t is continuous everywhere. T is actually continuous. Okay, so we prove this by using the previous part. So in the previous second part, we assume that t is continuous. Here we assume that this definition holds at the norm of t of x minus t of x naught less than or equal to epsilon for all x satisfying norm of x minus x naught is less than or equal to delta, which means that t is continuous at x naught. Okay, so using continuity at a single point x naught, we have established that we have chosen a y such that norm of ty less than or equal to c into norm y. So in the previous part, we assumed that t is continuous at a point x naught, and proceeding by the second part of that theorem, we have established that t is bounded and proved that t is actually bounded. And the first part of the theorem implies t is bounded implies t is continuous. So by part A. So t is continuous at a single point implies that t is a bounded linear operator. T is a bounded linear operator means t is continuous. So which means that t is continuous at a single point implies t is continuous everywhere. Okay. So this is how we prove the second part of the theorem. So second part of the theorem is actually this second part. T is continuous at a point implies t is bounded. This is the part you have to write in order to prove the second part of the theorem. So this is essentially the second part. Okay. Now, as a consequence of this theorem, we can quote the following corollary, 2.7.10 corollary. So which states that let t be a bounded linear operator. Let T be a bounded linear operator, then first part, for every sequence xn which converges to x where xn comma x belongs to d of t implies t of xn converges to t of x. So whenever a sequence is converges in the domain, when t is a bounded linear operator, its image sequence also converges. And the second part b is the null space n of t, which means set of all x element in the domain of t such that t of x is equal to 0. The null space is actually closed. So this is actually a consequence of the previous theorem. Okay, it is easy to establish this theorem. So let's move on to the proof part. Actually, we can prove this first part in several different ways. So the proof of the first part, we can use the theorem 1.4.8, which states that on a metric space a function is continuous, then xn converges to x implies t of xn converges to t of x. Here t is a bounded linear operator, t is bounded implies t is actually continuous. So t is continuous implies xn converges to x implies t of xn converges to t of x. From that itself we can prove this theorem 1.4.8. Okay, or in other words, given that xn converges to x, which implies norm of xn minus x tends to 0 as n tends to infinity. Okay, so this is the definition. Now we have to prove that t of xn converges to t of x. So norm of t of xn minus t of x by linearity property, which is equal to t into t of xn minus x. By boundedness, if t is bounded, t of x less than or equal to norm t into norm x. So t of xn minus x is less than or equal to norm t into norm of xn minus x. Okay, because this part is because t is bounded. Now from this part it is clear that we have assumed that xn converges to x, so norm of xn minus x is tends to 0. So which means norm of this part is actually tends to 0. T is bounded means norm t is actually a finite number. Okay, so which means that norm of txn minus tx tends to 0 because this part tends to 0. Or if you want to substitute norm of xn minus x as an epsilon, so norm of txn minus t of x should be less than or equal to norm t into epsilon. This norm t is actually a finite number because t is bounded. So since xn, norm of xn minus x tends to 0, by this part we can clearly understand that norm of txn minus tx tends to 0, which means that t of xn converges to t of x. So first part is actually quite easy. I have already told you you can use the previous theorem, that is t is bounded implies t is continuous, and use the lemma 1.4.8 to establish the theorem as well. 2.7.9 plus these two parts implies this part as well. So moving on to the second part, b. So part b, we have to prove that n of t is actually closed. In order to prove that n of t is actually closed, we have to assume an element in n of t closure. It is enough to prove that n of t closure is a subset of n of t. Clearly, n of t is a subset of n of t closure. We know that. So, if n of t is closed, n of t closure should be a subset of n of t, which implies n of t equal to n of t closure. So, this is what we have to prove. Now, take an element, x element of n of t closure. So, by theorem 1.4.6a, which states that for every element in an X closure there exists a sequence in X such that for every X element of X closure there exists a sequence Xn belongs to X such that Xn converges to X. This is what this theorem states. I think we have already discussed this. So X element of N of T closure implies there should exist a sequence, Xn belongs to N of T such that Xn converges to X. Okay. Now Xn converges to X implies by first part T of Xn converges to T of X. Okay. By part A. Now Xn is an element in N of T. So T of Xn is always equal to 0 because Xn belongs to N of T. For every element in the null space, its image should be equal to 0. So T of Xn converges to 0 means T of Xn is actually 0. Okay. So 0 sequence always converges to 0. Okay. So which means that T of X should be equal to 0. If T of X should be equal to 0 implies X should be belongs to N of T. So we have started with an element, arbitrary element in N of T closure, and we have established that X is actually an element of N of T. So X element of N of T closure implies X element of N of T. So which implies N of T closure, X is arbitrary implies N of T closure subset of N of T, which implies N of T is closed. So this is how we prove this theorem. Okay, so this is also a consequence of the previous theorem. Okay, so to sum up the second part, we have to prove that N of T is actually closed. So it is enough to prove that N of T closure subset of N of T. So we take an arbitrary element of N of T closure using the theorem. Every element in the closure corresponds to a sequence which converges to that element. So X corresponds to a sequence Xn which converges to X. Then by part A, T of Xn converges to T of X as well. Xn element of N of T means T of Xn is equal to 0, which means that T of Xn is actually a 0 sequence. So 0 sequence always converges to 0. So T of X, the limit of this sequence should be equal to 0. So T of X is equal to 0, which means X element of N of T. So X element of N of T closure implies X element of N of T. So which implies that this is X element of N of T closure implies X element of N of T, which means that N of T closure is a subset of N of T, which means N of T is actually closed. So I hope you understood. Thank you.